We're going to start off with the learning check here. This is sort of a review from previous videos in this particular unit. We're going to determine if these guys are acid or a base. Then we're going to find out if the conjugate acid, we're going to find out its conjugate acid base depending on what it is, and then determine Ka value if it's an acid or Kb value if it is a base. So let's start with the first one, HCNO. What you want to do is you want to take this and look in your reference sheet and look at all the Ka values. See if it's in this table, the dissociation constant for acids. And you'll notice that you can find it right here, the cyanic. And it gives you the Ka value too. So we know automatically this is an acid. So we're going to write that this is an acid. Now it wants to indicate its conjugates. So what is this acid become? It becomes a conjugate base, right? When it's added in water. So we're going to go ahead and plus H2O liquid. And that's going to form, since this is an acid, negative, because it has donated its hydrogen to water to form hydronium ion. Now, since this is an acid, we want to know its Ka value. And based on that table, the Ka value shows that it is 7.4 times 10 to the negative 4. Okay. What about F minus? F minus, you probably won't see it in this table. In fact, you might see the HF on the very bottom there, right here. Ooh, there's a pen mark over there, but there is a HF on the very bottom, but you won't see F minus. Okay, so you look at the base table, and if you look at the base table in your reference sheet, you'll probably notice that there's no F minus there either. But knowing that HF, the conjugate acid, is HF, F minus, and we can automatically tell that this is a base. Whether it's weak or not, it doesn't really matter for now, that this can act as a base. So if I were to add this in water, liquid, then this will form into HF. Since it is acting as a base, it's accepting a hydrogen from the hydroxide forming from the waters, becoming a hydroxide, and HF on this side. Since F minus is a base, it's asking for what is the Kb value. Okay, so you go in your reference sheet again and look for F minus, and you'll notice like the Kb value isn't there. But you know the Ka value of its conjugate acid. So we know that Ka of the HF is actually equal to 6.8 times 10 to the negative 4. It's on the very bottom of this screen here. I know it's kind of hard to tell. Let me see if I can go there. It's on the very bottom, but this thing keeps popping up. But you'll see it when it goes away. And there we go. And so what is Kb? Well, we know from previous lecture that the Ka and Kb have this relationship. If you multiply them together, it is Kw. Kw is 10 to the negative 14. And so therefore, if we want to know the Kb, we can divide the Kw with Ka. Kw is 10 to the negative 14, or you can write 1.0 times 10 to the negative 14. That'll be the same thing, divided by the Ka value, which is 6.8 times 10 to the negative 4 power. And that will give me the Kb. So let's go ahead and calculate that. 10 to the negative 14. I'm going to press enter and then divide by the 6.8 times 10 to the negative 4. Okay, so you got 1.5 times 10 to the negative 11. Well, it does definitely indicate this is a very weak base. But nevertheless, we were able to find Kb. Let's take a look at this example, H3AS4. So you'll probably know that it is right here, H3AS4. So we can tell this is an acid. It has the ability to donate that hydrogen. So we'll go ahead and donate one. This is this aqueous in water. So here's my acid. And if I were to donate this guy, it would become H2ASO4 minus, since one of the hydrogen has been taken out. So that's my conjugate base here. It's real plus, and that's my aqueous. So this is my conjugate base. This was my conjugate base here on the very first problem. This was conjugate acid on the second problem. Just wanted to clarify that. Okay, now it's asking for what is Ka value for this. And this one's easy because it's already written out for you. It's 5.6 times 10 to the negative 3. Where did I get that? It's right here. Okay. Now H2ASO4 minus. Okay. If you look at this, it can actually go both ways. This can act as an acid. So say if this was an acid, because it can donate it that hydrogen, it's a polyprotic acid. So because it has multiple Ka values, you know that it can act as an acid. But you'll also notice that because it can act as an acid as multiple, it can also act as a base and accept a proton. So let's go with the acid first. If it's an acid, if it's going to act like an acid, then if we were to put in water, it's going to become ASO4 and 2 minus, and then we have the hydronium ion. You put aqueous for all of these guys and then liquid for water. So the conjugate base would then be this conjugate base. So if it's an acid, I said, what is the Ka value? So this Ka value, if I were to go, and that's our second, it's when they deprotonate from the second Ka. So it's not the first one, that we did that for here, but it's coming from this point here, where in which it already has deprotonated. It already, one of the hydrogen has been came out, just one. So we're starting off with right here. And so the Ka value is 1.0 times 10 to the negative 7. Now say if this were to be a base, because the H2ASO4 can act as a base. If it was a base, that means that this plus the water will form into H3 because it's going to accept the hydrogen ASO4 plus hydroxide ion. So the conjugate acid would be this one right here. Now it says that if it was a base, then you need to find Kb value. By the way, this is A2 and then this is A1. Because that will come important to play when we do this problem. Kb is equal to Kb times the Ka is equal to Kw. And we want to know Kb. Okay, we want to know Kb since this is a base. And so we do Kw all over Ka and then Kb. Great. Now the problem here is you have to kind of think about it. Am I going to use Ka1 here? Or am I going to use Ka2 here? And that's where it comes a little bit tricky. You'll be using Ka1. So you're selecting the Ka that what it will become, because H3AS4 is, if you were to deprotonate, if you were to take one hydrogen, you're looking at that very first row right here, what it what it came from is this point here. So I'm going to use Ka1. It's really tempting here because the starting is H2AsO4 to utilize the Ka2. You're right, we use that if we're going in the acid, if we're treating this as an acid, but if we're treating this as a base, we're going to use a Ka value where it's going to go to, which is this one right here. So this would be 10 to the negative 14 divided by the 5.6 times 10 to the negative third. 10 to the negative 14, press enter, divide that by now 5.6 times 10 to the minus 3. I get my Kb value being 1.8 times 10 to the negative 12. Is my Kb value if this particular compound acts as a base. So a lot to review, right? Before we haven't even gone to the new concept, which would be the hydrolysis of salt in part 2.